to your presentation.
Thank you for the introduction. And yeah, indeed, it feels a bit like 10 years ago where Professor Richtgen was first giving a lecture and I'm giving the exercise afterwards. So today, I guess the exercise is to show you how to bring the frequency-based substructuring and block force idea into the development process for NVH of vehicles. And my talk's called Full NVH Predictions from Day One with hybrid NVH models. So that means coupling experiment and simulation models together. And to use especially benchmark structures, because I think this is something that is not yet used as much as it should be to solve problems. And I want to start my talk with a bold hypothesis, namely that an electric machine, which is achieving all the individual component NVH targets, just has too much mass. And I know this is a bold statement, but I'll explain you a little bit why I think this is often the case and how I think we could improve the process. So for that, I want to first give you a motivation, namely showing a little bit about the V development cycle that we use for NVH engineering and the integration in the car. And after that, well, I have really a few slides on the basics. We've heard a lot about the theory from Daniel Richtgen now, but from a high-level overview. And then mainly coming to the third point, which is building a model library of substructure components from benchmark testing. So starting again with the V model, we want to have a nice product. We start in the concept phase. And the first thing we do is we check on the customer level, what do the drivers want to experience? What does best-in-class NVH mean for the product we are designing? And then from this complete vehicle level, we need to go down to the system level with a target cascading, and finally also come up with targets on the component level, specifying all the individual vibration levels, airborne sound excitations, transfer paths, etc. Where we also have agreements which are, in fact, legally binding with suppliers, for example. And then afterwards, if we go into, let's say, the hardware phase of the development cycle, we get the first prototype data in. And well, we might get violations of these component targets. So then it's really the question, well, do we want to change something? Might be expensive. Later, if you integrate this component, you have all these goal conflicts between NVH, driving dynamics very often. Driving dynamics guys want the stiff bushings. We want to have the soft bushings. There's also some goal conflict sometimes between the efficiency of the electric motor, for example, which is the example I'm going to use in this talk. Also in our paper, you see something on the Audi SQ6, where you can see that they played around with the inverter control of the EDU to find a balance between NVH and efficiency in some speed ranges. I think that's quite interesting. And of course, I think you also have to mention this now, that you can do over-the-air updates also when the vehicle is already out at the customer to fix some sounds that you don't want. But also with sound design, you can't really fix a bad mechanical design. So you all know the push that we need to go to front loading and need to make also the important conceptual and architecture NVH decisions much earlier. And there's also trends we see at some OEMs where they want to get rid completely of the so-called confirmation build phase of the vehicle prototypes. So that also drives us towards we have to be much more confident about the concept that we develop, and especially if we have new architectures in vehicles coming up. So I want to talk a bit more about the target cascading process, really in a nutshell, how that is typically done. So, as I said, for the example of the electric drive unit that I'm showing here, we have our goal at the driver's ear. This is really what we want to achieve. The driver should have a comfortable ride. So, let's say in words, the target is we want to have a quiet ride without any tonal or harsh components. And what this means, for example, for the EDU, you've got some masking noise from the wind and rolling, and the tonal order components from the EDU, they shouldn't stick out of this masking carpet too much. So you might come up with a tonality parameter to specify what's the target for the sound of the EDU in the interior. And then, well, you already have to make an assumption, namely because you have to break it down, the sound in the interior into the airborne contribution. So what does the housing of the EDU radiate directly and which comes to the drivers here, and what goes over the structure-borne path. And this is already a mathematically underdetermined problem, right? You've got a single target, and you've got to give two targets to two paths. So this is by definition mathematically underdetermined. There's infinitely many solutions. You got to make some assumptions. And if you go then even further, you need to cascade it down. So you've got individual transfer functions for the airborne excitation. There's a little bit of a secret sauce and some, let's say, culture at each OEM, how they do that. And the same goes for the structure-borne transfer functions, where you just know maybe from experience, from the previous cars, how they look like. And then you also give individual targets for the structure-borne excitation. So that could be vibrations at the mounting points in each direction, or forces at the mounting points in each direction. And that's what you finally give to your suppliers. But the thing is, when you don't have the car yet, you're making a lot of assumptions, and you have all these interdependencies which you're trying to freeze in this early stage, which is not really there. So you have this, when you do this target, you have this horizontal interdependency. So the whole EDU target depends on what is actually going to be the rolling noise in the vehicle, what's actually going to be the wind noise. And if they do a better job than they should do, this is a problem for the EDU guys. So you should always hope that your colleagues from the road noise departments don't get much better than they need to. Otherwise, you're going to hear the EDU. And there's, of course, as I mentioned, this other interdependency, which is, I call it the vertical interdependency here, namely that, as I said, you have a single target at the driver's ear, and you want to break it down into a large catalog of individual target curves for all the components and all the individual forces. And that is, by definition, mathematically underdetermined. So some people make an assumption that just all the transfer paths stay the same in their individual weighting compared to the predecessor vehicle. There's optimization methods. I think there's clever stuff with solution spaces going on right now, but that's not my topic here. The main message I want to give you is that this target cascading process is, in my opinion, important, but it's never really perfect. And I would argue that it's better to have a process which can go directly back up to the driver's ear and see what things mean. So what this leads to often in discussions between, let's say, an OEM and a supplier of an electric drive unit is, well, okay, we have these targets. So this is just one example. This is for a car transmission. And you have these yellow target levels at different speeds. This is for a single order of the transmission. And you can also see that for increasing speeds, this yellow bar increases because the wind and the rolling noise increases. And in red, you see the measurements at a coupling point measured with an accelerometer. And here you see, oh wow, there's a violation of the target at 3,000 RPM at this one coupling point. And now really the whole fun story starts because then the supplier says, well, we can fix that, but we need additional budget, we need additional weight on the transmission. This is something you want to think about if you intend to produce 1 million units of it. Then the discussion goes, well, I think the targets are too strict. Is it really a problem at the driver's ear? Unknown, we don't have the vehicle yet. The OEM is raising the question internally, well, what's actually the status of the masking noise? Is this really a problem? Also, it's a question, is it maybe cheaper to fix the issue with just changing something in the mounting system, or can we actually add active sound design to just mask it a bit more? And maybe the most important question of all, who takes the risk in terms of budget if something goes wrong and we just if we continue knowing about the target violation and something goes wrong. So what I want to argue for is that while it's still important to derive these component targets, I think it would be much more helpful to have a full NVH prediction at the driver's ear, actually from day one, and to set up a process where you can have an instant digital NVH twin of your car, of the concept you're currently designing. And for that, you of course need really good data quality from your predecessor vehicles to make these decisions. Do we want to continue knowing about a single target curve being violated? And have a sophisticated change management process of your full vehicle model, so that as soon as new data arrives, we get in the first test data from the suppliers, we get in updated finite element models of individual components that we can change them like Lego blocks, and you all see where this is going. This is going towards substructuring to see if this is actually going to be a problem at the driver's ear. So this is what I want to show, and want to go into the basics a bit with how we can create these digital NVH twins from substructuring. So basically you have your simulation models, your test-based models, and you want to couple them on the interface to create a hybrid model of the full vehicle to get the full transfer path from the source all the way up to the driver's ear. And as Professor Rixson has already shown, you can use testing to derive experimental models, and you can use the virtual point transformation. So you basically have the geometry of your component. You place your sensors, you place your excitation points where you excite with a hammer or a shaker. And then you basically, from knowing the geometry, you build these relations, these transformation matrices, and project everything into the virtual point. And that is, in principle, compatible with simulation, where you have these RBE2 or RBE3 spider elements, and you can enforce this compatibility equation, namely that they do the same vibration and that the forces are in equilibrium at this point. And thereby you can couple very flexibly, actually, simulation and test-based models to each other. And this is an example from still my PhD thesis that I brought. This was about the electric climate compressor in a car, which I show because you can see how flexible this is, how you can mix the models. So the climate compressor was basically modeled as a rigid body. That was the simplest and best model in the frequency range of interest for the climate compressor. Then you have a experimental model of the rubber mounts, or this could also be just a parametric analytical model if you're still in the concept design phase and thinking about what do we need in terms of stiffnesses there. There was a finite element model of a pure metal intermediate carrier. That was basically an isolation mask, just a metal structure. Finite element is perfect. And then a transfer function of a mule vehicle. So this was one of the predecessors which was used to carry this concept. And then it was actually built up, this assembly, and that's what you see at the bottom here. This is just one single FRF curve where you see the actual measurement in blue, and in black the prediction with substructuring from all the individual components. And what you also see there, what I find interesting, is that also here at the higher frequency range, I think this stops at 1 kilohertz, that's because the bushings were so soft, you couldn't get enough energy in with your excitation equipment, so it's really noisy. But with substructuring, you model each structure with a good signal-to-noise ratio, or it's just from simulation, and you can even get cleaner predictions up to high frequencies. If everything goes well and the interface problem is well conditioned, I was a bit lucky because the bushings were quite soft, so it's kind of a real-world way to do regularization on the interface. Anyway. So the last thing you need, you then have the transfer path from the source all the way up to the driver's ear, and the last thing you need is a way to describe the source. And this is, as we heard, can be done by blocked forces or some way of equivalent forces. The same is for the airborne sound. I'll go into this in a bit. So finally, you have what I said at the beginning. What is the target? You want to have actually a prediction at the driver's ear as early as possible, because that is finally what you're selling to your customer. You're not selling a target curve on the engine, you're selling a sound at the driver's ear. Good. So, yeah, and you can then make a, in my opinion, more justified decision if you want to change something on the system, or if it's actually just a violation of a target curve, which doesn't really matter at the driver's ear. Good. So, what do I think makes sense to do is something that everyone is already doing, and also we at FEV are doing quite elaborately, namely benchmarking. So you get benchmark vehicles, you see outside the door, you see the Xiaopeng 9, to find out what is actually the current status of the market, the best-in-class NVH. And we have a benchmarking program here where we basically monitor the markets, take the most interesting technical concepts, get the vehicles in, and give you quite elaborate benchmarks and store that in a database called Karat. So what we do basically, this is a more recent roadmap. This was from 2025, is that we have 3 benchmarking centers worldwide, one in Europe, one in China, one in the US. They monitor the market and take the most recent models from the local market. And then we do benchmarking basically up on our own initiative or on customer request. And this is done in a, we call it level 1, level 2, and level 3 benchmark, where basically level 1 means the what, so what the driver experiences. In terms of NVH, this means we drive the car, we do measurements at the driver's ear at a certain test matrix, different driving conditions. We do subjective evaluations with our NVH engineers. And that's the level 1 benchmark in terms of NVH. And we do that for all the other attributes of the car. The level 2 would mean kind of after the what is kind of the why. And for NVH, this means we do a more elaborate instrumentation. So we put a lot of sensors on the individual components, more microphones. So say at the EDU, at wheel knuckles for the road noise, etc. And at level 3, then it's really the tear down of the car. So where we disassemble it, where we do elaborate documentation of all the parts, also a estimation for what this costs and how it was produced and why it is designed in a certain way. And so this is the overview of the benchmark program, but this is, for me, this was very natural to say, hey, we should use this for NVH. We should, if we do this anyway, we should build a model library that gives you kind of modular models of all the benchmark vehicles. So concretely, this means on the example of the EDU, what we want to have a source model of the EDU. So we need to have something that describes the structure-borne sound. Well, that's equivalent or blocked forces. We need to have something for the airborne sound and something for the passive dynamics. So going into this in a bit more detail, say we are at a level 2 benchmark. This is the Audi SQ6, and we do operational measurements. This is an all-wheel drive acoustic dyno of the car. We take often a 3D scan of the EDU in this case, because it's a benchmark car. Audi wasn't nice enough to give us the CAD geometry, and even if, we wouldn't be allowed to use it for public purposes, but this is a car that FEV bought. Okay, so we have the geometry, we can place our measurement equipment at the coupling points, we can do impact testing, and then get basically an operational signal from this test matrix we do, and we have the transfer function that we measured. And as you've just seen, we can compute the blocked forces, which describe the source, so the EDU excitation, in all these different driving states that we test by computing them with the so-called in situ method. The other thing that goes into the database is the airborne sound path for the EDU. If we do just level 2 testing, we can at least take out the airborne share by a transmissibility-based. Take out the EDU. This is what you can see here at the top right. We can either measure the sound power if you just have a single airborne noise target, or we can even take equivalent monopoles and describe the source with that. So some monopoles at the surface, you can derive them just with the same kind of active noise cancellation analogy that Professor Rickson has just shown for the blocked forces. It's mathematically exactly the same. And then as the last one, you want to have the passive dynamics of the EDU. So if you want to virtually couple it into another receiver, you need to know what this is doing, how this is interacting with the neighboring components. So basically, we do this impacting. We hang it up free, right, with rubber bands. And you also do quite a few data checks. There's going to be more on that in the next talk, I think. But basically, there's a lot of things that go beyond just classical coherence, which is that you look at the operation of deflection shapes, if all the sensors are applied correctly. There's this virtual point consistency that also Daniel Rickson has talked about. And also the later talks will talk about this. There's passivity. You don't want to have negative damping. I was sometimes happy that I found a perpetuum mobile, but mostly it was a measurement error. So you want to check that. Also the symmetry of the matrix in order to have quality data to go into this substructuring library that we're building. And then if we take out the car, the next thing is the rubber mounts. Daniel Rickson has already explained this method of attaching transmission simulators to the rubber mounts. So these are basically just rigid blocks, which you can describe as a rigid body just from the CAD model. We took your mass, your rotational inertia. You decouple them with decoupling after impact testing on this. And what I really want to show why this is important for electric drive unit sound is here's the obtained dynamic stiffness of 3 different mounts, which have a nominally different constant stiffness. But you see that here in the higher frequency region, you all of a sudden have continuum resonances in the rubber itself, and that can cause quite a large stiffening of the bushing. So it can lead to a fact where actually the soft bushing, so to say, is behaving much stiffer than the hardest bushing, and that is, of course, in a frequency range that is interesting for EDU sound. So you want to have that in. And the next one is you need to have a model of the virtual vehicle. This is the most difficult one to simulate. So in an early project stage, you might take out a vehicle which has a similar architecture to the one you're designing. And what we do is, well, as I said, we dismount the EDU. We again do a 3D scan of the compartments. We define the virtual points where you can couple your new concept or the other EDU. Measure the transfer functions at these coupling points for coupling, and also the transfer function to the cabin. And the last thing you need is also the masking noise for the example of the EDU. So we measure we have scatter bands for the rolling and wind noise masking at different speeds. And from that, you can also judge, okay, well, if I virtually couple my EDU into this receiver, is this going to be audible or annoying or whatnot? So that's the whole idea. Like looking at this is how we can take apart a benchmark vehicle and build a modular model of that and be much earlier with the predictions at the driver's ear instead of just looking at single target curves for the component. And this brings me to the summary. I don't have enough time to show you the Audi SQ6, but that gives me the reason to make you curious about the paper. As I said, we've seen when we did this on the Audi that there's quite an interesting solution that they found between the EDU excitation, the inverter control, and the vehicle transfer functions. You can look at that, but mainly my message is that FEV has started to build up this database for frequency-based substructuring, and we're building this for e-motors, transmissions, mount models, vehicles. Also, if you are interested in some models, we can talk. And this really helps with getting this workflow that I described, which would be desirable to fly, because you can then, in an early stage, take benchmark models for the things which are difficult. You just take a receiver and you insert your concept in that, and then every time you get new data, someone has updated a model, let's say the rear axle carrier or so, or there's new mount models, measurements from the suppliers, or the EDU supplier has simulation data or first test data. You can easily update that into this modular model and basically substructure it together like Lego blocks. And instead of looking at just gazillions of curves on the component and trying to judge if this is going to be a good EDU sound or not, you can actually listen to that at the driver here and then keep your let's say your decision process for NVH decision ready at all the stages, and especially in the early stage. And that was it.